thanks for coming in. Hopefully that was a nice little buffer for some latecomers. So I'm presenting on Clover's. Current working tagline is search as sport. But before that, I will tell you a little bit about who's been building it. Bin Studio, it's some friends, Alan Wu, myself, Everett Williams, Nicholas Court. The last month or so, I've been working with Corey Levinson with cadCAD software, product out of block science for simulating different models. And the whole project is supported by the Ethereum Community Fund. A little bit about myself. My name is Billy Rennekamp. I'm involved in a lot of projects. I kind of can't help myself. And anything that's sort of slightly interesting, you can very easily nerd snipe me. As you can see, I've been interested in working with Clovers.Network. The last few months I've been working with Aragon Black, implementing something called batch bonding curves, which are front-running resistant dexes. I've been working with Gnosis PM on that topic as well. I'm the author of EIP 1633, the Refungable token. I've also built ENS Nifties, and last but not least, Meme Lords, the curation market for memes. So Clovers. What are Clovers? At their core, they are a proof of work algorithm. They are proof of search. So instead of using traditional hashing mechanisms like you see in proof of work on Bitcoin or Ethereum, where you're just sort of scrambling a random number, mainly the hash of the last block or whatever, and hoping that it begins with a bunch of zeros. With Clovers, you are playing a board game called Othello or Reversi. And you use the rules of that board game similar to the hashing mechanism that you'd see in other proof of work systems. If you're not familiar with the game, it's very, very simple. There's this very slowed down GIF of it. But essentially, you begin with these 4 tiles. You, if you're the white player, you surround a black tile and you flip it. If you are the black tile, you do the opposite. So here the white player flips it. Now the black player will go back, flip the next one. It's a nice game because it has a very, very simple and limited rule set, but the game tree is extremely large and complex. So you also know that there's only going to be a maximum of 60 moves at any given board. It's an 8x8 grid, so that's 64 pieces. Every single move must progress the board until there's no more possible moves, and the game finishes. So while you have this very limited computational space, you have a very, very large game tree. It's never been mapped out in entirety, and it's very convenient for what I'm calling proof of search, which is that you move down this massive game tree, and you end up on a final board state. But because the board has changed so drastically every move, there's no real way to figure out how you got there. So if you were to start from the other way and say, this is a final board state, like how do I get to that? It's pretty much impossible. And so it's very similar to something you might be familiar with in cryptography called a trapdoor function. Trapdoor function is sort of like a hash algorithm. It goes through a process and you have some end result, and it's impossible to basically start from the end result and get to the beginning, but it's very easy to get from the beginning to the end result. And so with the game Reversi or Othello, you have this really convenient trapdoor function. On the right side, you can see something similar to a private key, which are, in chess notation, the moves required to play that board game. F8, F4, these are all sort of squares on the board. And at the end, on the left, you can see the end result. All the white pieces basically blend into the background. This is because the white player won. So you have this sort of version of a public key, which is, again, these are both approximations of what a public key and a private key are, but they serve in similar functions inside of this game. So this is the hexadecimal notation representing this actual board, which is also used as the ID number for these. But a little bit of background on where this all came from. I mentioned that it's a really convenient game because it has simple rules, but a very large game tree. So it was interesting to early AI researchers. They had pretty limited computing capacities, and so the first sort of times people were questioning, like, how do you make an intelligent being? How do you make intelligent software? Let's look at board games. Let's look at checkers and chess and things like that. This was convenient because it was so easy to model, but because you couldn't do brute force. You couldn't just look ahead every single step of the way because there was just too many options. You know, no computer even today would be anywhere near possible mapping out every possible move. And so you started thinking about like intelligent heuristics. If I were to do this at this point, how do you evaluate the board and stuff like that? So of course it comes up in computer science school classes. I was confronted with this in the class, but I was actually in the art department, And so instead of sort of following the strict rules and trying to find a player that would win, I was dealing a lot with these ideas about the player, the cheater, and the toyer. So in any given game scenario, if you play with the rules and with the objective, you're a normal player. If you play with the objective to win, but you break the rules, you're a cheater. If you break the rules and you don't care about the objective, you're a spoil sport. But the fourth quadrant is that you play with the rules, but with a different objective. And this is sort of like goes hand in hand with a lot of hacker ethoses, sort of using the system as it's built, but not for the purpose it was built. Goes into a lot of artworks you've seen, sort of misusing or reusing or appropriating materials for its own use. So this is, of course, on my mind, and I decided to approach this assignment of building an intelligent player the same way. So I decided to try to find games that ended symmetrically, but this had its own sort of challenge, and I sort of stumbled upon what was proof of work. So this sort of had the aura to me of like similar artworks because they accrue sort of energy through the idea that they're difficult to find or that there's sort of energy or time that went into the process, where it's you just presented with the image itself, it doesn't have that, but the context provides this weight. So I started making artworks out of these. These are pretty old ones. In this process, I got involved in the Othello community. This is me competing on behalf of Germany in the 2013 World Championships in Stockholm, Sweden. That's just a fun tidbit. I started looking into tournament databases. These are all from a database called Thor, which is all of the professional games. So Mark Tastet was the 1992 World Championship, and those I can't read. But so I started sort of going down this process of like trying to find these end results, and sort of celebrating that as an aura or proof of work. These are the boards wrapped around spheres and leather. This is at the Proof of Work exhibition at Schinkel Pavilion last year. And this is sort of some ongoing work about using turtle shells. But it was always sort of the idea of like, how do I produce more of these things? Like if I were to maybe turn this into an incentive game, if I were to make this an app where it's actually you have users getting rewarded for finding these things, because after sort of trying the look ahead, depth first search process, it's extremely computationally intensive. And I realized that actually, and after exhausting all of the databases, that it's actually a much better technique to just play random games, and like every now and then lightning strikes and you get one. So the more people I could have playing these random games, the better, sort of like a botnet or something like that. So create an incentive for people to be finding these things, and I would be able to produce much more of these proof of search results and do what I will with them. So this sort of started me down the process of building it into a game. And when I stumbled upon Ethereum and Solidity, I sort of struck that this could actually be a real currency and not just points inside of a game. So we built the first prototype last year. We've built a revamp on the UI, polishing a next phase that we will launch in August. But here's a quick sort of intro to how the game works. I guess, did you get any response?
He is coming, but on his way.
This is sort of a walkthrough that you'll be presented with in the future, where you can see that you can create Clovers in your browser. So this is one getting mined in real time. Nice job. Make another. Keep going. That guy's kind of good, actually. Third, and you can continue. So your Clovers are saved in your basket. And now let's say you find a symmetrical Clover. So Clovers with symmetry are rarer, and if you find one, you can claim a reward. So this one is calculated to be worth 6.23 Clover coins, and you can exchange them for Ether. This is on the Rennekamp testnet right now, where Ether is cheap, so the price is pretty high. You would get $6.92 worth of Rennekamp Ether for this one. So here are the Clovers that you found earlier. These ones aren't symmetrical, but you can still collect them or sell them. In this process of sort of only searching for the symmetrical ones, I kind of came across this much more engaging phenomenon of sort of the noise that comes through this. It's a bit like pareidolia or something like that, finding shapes in clouds, where you have this source of noise, and actually through the process of contextualizing them, you're able to sort of create meaning or value outside of what is essentially noise. So these asymmetrical clovers have very much a role inside of the game and space itself. Then you have your profile. You have the marketplace where they get bought and sold. You have the garden, which is where you sort of watch them created in slow time, where you would look for the asymmetrical ones, add them to your basket. But you also have something we call the Clover pig, which is sort of like a truffle pig. It sniffs out rare clovers in the background. So this is sort of mining hardware done in the browser. And then you would be plopped into your garden where you could see them grow. So just to scroll really quickly to give you an idea of what sort of images you're looking at. This is kind of nice. Coming through this sort of generative process. That is a very quick tutorial. I'm going to go over really quickly some of the pieces in it, and then I wanted to open up for discussion to get some, I'm sure, what are still needed clarifying questions. So Clovers are first and foremost non-fungible tokens. This is the format they take place in. And if you're not familiar with that, this is a standard of interoperable contracts on Ethereum. It means that any third party can walk up and understand exactly how to interact with your contract, with your assets, with your non-fungible tokens. And those are all really great because it allows that interoperability. They become self-sovereign. You can have potentially digital scarcity, and they can be used for authentication and things like that. So I mentioned that search reward. This is based on the Symmetry, and these are paid in an ERC20 Clover coin. You can see here examples of all the different types of symmetry inside of this space. That would be x equals 0, y equals 0, rotational symmetry, x equals negative y, x equals y, all of these on sort of Cartesian planes. Clover coin is attached to a bonding curve. This is so that all of the users aren't sort of locked in a way. I got excited about 721 as a standard and ended up working on it with a lot of other projects because it was useful inside of Clovers. Then for the same reason, I wanted to be able to offer a marketplace to all of these users so that they could actually cash out if I had a reward. When I found out about bonding curves, sort of this market maker that offers this exactly, that sort of drove me through that whole space. And so we're using it inside of here as well. Ether is currently the collateral, and the price per token is dictated by how many tokens are in circulation. If you're not familiar with a bonding curve concept, this is a contract who is always willing to buy or sell tokens to you or from you. And whenever you send it money, that money is held in the contract. It's preserved there, and it's used to buy back tokens at a further point. The rate of exchange is always dictated as a constant on this curve. And so the more coins in circulation there are, sort of counterintuitively to supply and demand, the more expensive the coin is. But actually because the coins in circulation are representing the demand itself, the more coins in circulation, the more the demand is. And so the more the demand, the higher the price. So this is what I want to talk to you guys about. But maybe it's better to stop already, or maybe I walk through really quick what these things actually are and a user story, and then we can go to a discussion. So in this scenario, you have a player. You have the garden I mentioned, you have the pig I mentioned, and you have miners. The player might use the pig or the garden to find clovers. They'll take rewards for symmetrical clovers. They might take risks on subjective values. This would be the asymmetrical clovers, or if the reward function is willing to pay you some amount, but you think it's worth way more than that. They also might add contextual value, like a name, comments, albums, likes, something that would sort of designate this clover to have the assets that you seem to see in it. Like if you see a face in a cloud, you would need to write, there's a face in this cloud for somebody else to be able to see it. The garden I mentioned is the sort of slow mining. It shows all types of clovers, asymmetrical and symmetrical. There's more variety and potential for subjective value here. This is the pareidolia I mentioned, like watching clouds. Then you've got the pig I mentioned is the fast mining tool. I mean, it's a lot faster than the garden, but it's still restricted by your browser. It's a JavaScript worker, so it doesn't mess up the front, but it's multi-threaded, so you can get kind of good performance. This searches only for the symmetrical clovers, throws away all non-symmetrical clovers, and it's mostly good for sort of objective value symmetrical ones. And then you have the miner. A miner is somebody you can imagine that as soon as they see there's a reward available through this contract that they can make money from finding these things, they maybe don't care about the contextual value. They don't care that I made art about this stuff at one point. Like all they see is that there is a 30-cent profit every time they put this exchange in. They will try to maximize that. So they might use the pig or some other fast mining technique. They will always release the Clover in order to receive the reward. They'll never pay the fee to keep the Clover, and they'll stop if the reward is going to be less than the cost of gas to actually receive it. So you can think about these user stories. There might just be, very simply, a player who finds a Clover, whether from the garden or the pig. They like the Clover. They burn a fee to keep it. So the Clover itself is a non-fungible token. The fee is that ERC20 I talked about. You must burn some amount, which is dictated by the contract. And in doing so, you are able to keep the Clover. Then it can go on its merry way and do whatever it wants. Story 2 is a player might find a Clover and see potential in the Clover. Either it's symmetrical, but it's only paying out 10 cents, whereas they think it's worth $1. Or maybe it's asymmetrical and it's the face of Jesus Christ. They know that this is more valuable than what the contractor is willing to pay for it. They might add contextual value by sort of addressing those features, comments, albums, and likes. And then they might move it onto a market where they might actually capitalize on that evaluation of the value. A third story would be the player or the miner finds a Clover. They release the Clover. This means that they exchange it for the reward. If anyone does decide ultimately to buy that, that amount is burned. So you see you have these two forces going against each other for the token. You have a token sink whenever the token is burned, and you have inflation from minting. So this is an adjustable bonding curve, where you might think of a bonding curve typically has exactly the right amount of collateral to pay out the tokens that are in existence on that curve. With an adjustable bonding curve, that curve can constantly change. So if you decide to mint a bunch of new reward tokens, all of the other tokens in existence will be basically watered down in their value. Nobody can get out as much money as they had hoped for like at the initial moment. This is how you can sort of leverage having a token. This is the reason why there's a token at all, because you're able to use it to reward people. However, if you just have runaway inflation, all of the value will constantly drop and no one will want to interact in the system at all. So you have all these token sinks. This is in the situation when somebody wants to keep the Clover, or if somebody buys it on the market from the contract, that would also be burned. You have to imagine that people would probably want to just take the reward over paying to keep it more often, and so those fees need to be proportional to each other. There has to be enough burning of tokens to make up for the minting of tokens. So before I go into cadCAD and modeling the system, maybe it's a good time to stop and talk about what Clovers does itself.
Questions, right?
Yeah.
So is there a bonding curve for each Clover or for all Clovers together?
So there's a bonding curve for all Clovers together attached to the Clover coin. There's also a mechanism in place that I will be de-emphasizing, where each Clover itself can have its own bonding curve attached to it. And that's what the refundable token is. That is a very exciting concept, but obviously this is a very complicated system, and I felt for the first release it is just too much. But I'd love to talk about that more. I also have it in the slides later to bring it up as a topic of discussion in general, whether for use in this or others. I mean, my logic for using it here was sort of this process of valuation must fluctuate wildly. Like, how are you supposed to say what something is actually worth in this context? Like, you're probably similar to that conversation with regard to art. This is the whole "my kid could paint this" conversation. And so in a context in which one person might have an extremely high valuation of an asset, but nobody else is willing to sort of buy it at that price, you might decide to move it into a refundable token, in which you'd basically be able to sell shares for it. So where it's unlikely to find a single buyer who has the same approximate value of it, it might be more likely to spread that into a larger group by creating basically a sub-token or a refundable token on top of that asset. That's actually clear to everyone? Really? Who has problems with it? I came here because I want people to poke holes in this. There's many places to poke holes, so I welcome it, please.
Did I get it right that deciding to keep Clover is a burning event?
That's correct.
But a fee is paid for that.
Yes,
Why?
by the user. So I see this Clover just because I like it, like user story 1, or maybe user story 2, where I think I could actually make a profit off it. I decide to burn some amount of Clover coin in order to receive it as the NFT. So even though I found it, that gives me the right to make a decision of what to do with it. It doesn't necessarily give me the right to just keep it straight out. I have to then, at that point, decide, am I going to exchange it for a reward fee and give up the Clover, or am I going to pay that reward fee times some amount in order to keep it?
But doesn't this go to the logical conclusion that then when you buy into those Clovers, the tokens sink and then the price sinks, but the value actually increases because there's more demand for Clovers? So it's
When you burn the Clover coins, the value of all the remaining Clover coins should rise. So every time you actually pay for a Clover, you should be increasing the value of the entire ecosystem. You should be raising the value by burning money.
okay, but it's going with the bonding curve, so it's going down, right?
But it doesn't change the collateral in it. So bonding curves only move down when you remove collateral with that burning event. But because you're just burning it and you're not accepting collateral, the value of all the other ones increase. And that's what the adjustable bonding curve is, which I think has a lot of uses in a lot of different contexts.
What does the contract sell the Clover for on the market?
So right now, it sells it for 10 times the amount, but it's a rather arbitrary value. And that's what the use of cadCAD is sort of supposed to help with. There's a lot of sort of parameters in this whole thing, which were basically arbitrary. And I think it's sort of like a ethical requirement to try to run some basic simulations on what are mostly arbitrary parameters that I think are in the token engineering space.
My follow-up to that is, why would a user buy this Clover on the market then?
So it's already been discarded, right? Chances are it was discarded by a miner who would discard it no matter what. It could have also been discarded by a user. But if it's discarded by a miner, you have to think that they're not applying any of this value judge that a human might be able to. They aren't able to evaluate beyond what is the current price on the reward function. And the sort of long game of the value of this is that there's a proof of work that's happening with humans on top of this proof of search, which is sort of proof of contextual value or something like that. And so if one got sort of misallocated in the first run and put onto that marketplace, it might have a second life when somebody realizes actually it is worth this or maybe more or something like that. I mean, obviously, I think this ratio of ones which go to the market because of the bank puts them there versus ones that are actually bought from the bank must be very low. And so this provides sort of an interesting UI question of like, which Clovers should you show a user when? Like, is this just exhaust? Is this just trash that's coming out? Or is the whole point like harness the exhaust because inside of that rough there might be diamonds here and there, and that's its own sort of human-centric game.
How much time do you have to decide if you want to keep the Clover?
As much time as you want. So I showed you that garden view. Mm-hmm. That's sort of like the human speed version of it. So that one you can scroll at whatever speed you want. You could stay on the same screen and evaluate the Clover for the rest of your life. The pig will only show you symmetrical ones. So they're only doing one very specific version of this mining for you. But the garden is where you're supposed to spend time as a human sort of evaluating or just passing the time and watching clouds pass by.
But someone else could like take the Clover.
Someone could. These ones that are mined on your browser, so you're the only one who sees them up to that point. And the benefit of such a large game tree is that chances are nobody's going to find that one in the next however many minutes, hours, days. Sort of like the grain of sand thing.
Have you thought of utility for this in some sort of real-world applications?
It has a lot of similarities to CAPTCHA. I'd say it rhymes with CAPTCHA, but I don't think that it has as easily extractable valuable in that context. There are other versions of it I've thought of, but most of them are when I've followed down that train of thought detracts from some other value point. But yeah, I mean, if you have concepts or ideas about it, I'd love to hear them. Is that okay?